So, starting off our series of Unit 4 lectures, we're going to go through it in 3 parts. Today we're going to start off by looking at motion, which will include momentum, impulse, circular motion, gravitation. Okay, so part 1 of our Unit 4 lecture. Starting off by looking at Newton's laws of motion. First law, an object will continue at rest or continue moving at a constant velocity unless acted upon by a resultant force. Second law, the rate of change of momentum of an object is directly proportional to the resultant force acting on it, and the change of momentum is in the same direction as the force, and we mathematically write that as F is delta P over delta T. Third law, when body A exerts a force on body B exerts an equal and opposite force on body A. So those are the first 3 laws. I'm going to give an example for each of those. I'll show that again, because I think you may have missed it. In each case we're using the same car, right? So starting off with a car moving at constant velocity. It's got a thrust force and a drag force, and because it's moving at constant velocity, T equals D, therefore the resultant force is 0. So there's no resultant force acting on it. It continues at constant velocity. Second law, this is a car braking, so now it's got D, no T, and it's got a friction force acting against the motion. So the resultant force was 0, because T was 0, minus D plus FR. Those 2 terms in brackets there, so they're both negative. And that's equal to the change of momentum. Now, for the change of momentum, what I've done is I've used mv minus mu, and v is 0, so this whole term becomes 0. So we've got essentially got minus mu over t for that equation. For Newton's third law, the Earth pulls the car down, the car pulls the Earth up, and the road forces the car up, and the car forces the road down. Okay? Now those are the 2 Newton third law pairs. So W is equal to the gravitational force of the car pulling the Earth up, because the car has mass, the Earth has mass, so they're both attracted to each other. And the 2 normal reactions are equal to each other. Now, I haven't drawn the other 2 forces on there at the moment. I still only have this normal reaction of the road on the car, so I've called that NC for normal reaction acting on the car, and the weight. Okay? What normally happens when you have a situation like this, you may be asked to draw the forces acting on the object, is that students think these are the third law pairs. They're not. They are equal and they are opposite, however they do not satisfy Newton's third law because they both act on body A, the car. So you have to identify the body B's. There's actually 2 of them, and they are, as per this description here, the Earth and the road. Those are the 2 body B's. So body A is the car, body B is the Earth in one case, and the road in the other case. So if I draw the other forces on, we would have this. There's a normal reaction acting on the road, and there's a gravitational force acting on the Earth. Note also that the Newton's third law pairs are the same type of force. Both normal reactions and both gravitational forces. Weight is a gravitational force. So there's also that check as well, whereas normal reaction is not the same as the weight. Okay, so there's some examples. Momentum and impulse then. Momentum is mass times velocity, P equals mv. Impulse is a change in momentum, so delta P, and we can work out the change in momentum from mv minus mu. From Newton's second law, which is that the result force is equal to the rate of change of momentum, F is delta P over delta T, and if you rearrange that, delta P is equal to F times delta T, and that's saying that impulse is equal to force times the change in time. Impulse is equal to force times time. Impulse units, you can either write as kilogram meters per second or Newton seconds. Now, let's say you've got an object, it's moving with a velocity, has mass, so therefore it has momentum. If you want to bring it to rest, then your final momentum is 0. There's going to be an impulse bringing that object to rest from whatever momentum it has to 0. There are two ways that you can do that, and you can see them illustrated mathematically here. You can either use a large force, and then, in which case you'll bring that object to rest quickly, small time. Okay, so large force, small time, giving you a certain value of delta P, whatever delta P is required to bring it to rest. You can also use a small force to bring it to rest over a longer period of time, so delta T would be bigger, still giving you the same delta P value. So if I apply it to the car again, the car can crash into a wall. That wall will exert a large force on the car, therefore the car will come to rest very quickly, and it's going to be a very painful experience as well. Now let's say the driver actually sees the brick wall, then they start to apply the brakes. Smaller force, takes longer to come to rest, okay, but hopefully before they actually reach the wall. So momentum and impulse. Together with that you have force-time graphs. Force-time graphs may look like this. This may be for something such as kicking a football. Kicking a football, and the force is not constant whilst the foot is in contact with the ball, right? Now, kicking a football happens over a very short time from what you can actually perceive of it, but actually if you break it down then you would get something like this. So the force is not constant, and there's a max force, so that's our maximum force. At that moment here, your foot is causing the ball to accelerate by its largest amount, so you get a maximum acceleration that is related to that. And then you also have the area under that graph is the impulse, delta P. You're often asked to estimate the impulse from a force-time graph. You have to add up quickly that area. Conservation of momentum then, the principle of conservation of momentum. Total momentum before a collision is equal to the total momentum after a collision, provided that no external forces act. So here's my example here. B is stationary and A is colliding with it. A has an initial velocity UA, UB is 0. So the total momentum before, this is the initial conditions of the collision, is equal to the mass of A times UA plus the mass of B times 0. So the total momentum before is equal to MA UA. And after the collision, they're both going to move off with velocity VA and VB. So the momentum after is equal to the mass of A times VA plus the momentum of B times VB. I wrote this in here because, according to the principle of conservation of momentum, the total momentum after is equal to the total momentum before. So because we have this term for the total momentum before, that's equal to the total momentum after. Okay, so then they move off. Now you notice that MB was smaller than MA, so it moved off at a larger velocity than VA. An example of the conservation of momentum. Oh, if it works. Hang on a minute. Let's see if I can try that again. Okay, this is an example of conservation of momentum. Slightly more interesting than my mundane one that I just gave you. I'll just see if it actually shows this. There you go. Pay attention to what they do next.
Trust me, rotate the turn 82 degrees. Fire!
They're trying to shoot down that other gun.
No, they're trying to flatten the tank.
You can't fly a tank, fool! Rotate 16 degrees! Fire! Rotate 34 degrees now! Aim! Break turn full front and wait! Look ahead!
Okay, so that was a much more interesting example of conservation of momentum. Did anyone spot what it was?
The recoil.
Yeah, that's absolutely right. The recoil of the tank. They were firing out the projectiles from the tank barrel at high velocity, so it's got momentum. But the total momentum of the system before was zero. So in order to maintain that total momentum of zero, the tank has to recoil. So that, therefore they could aim where they were going to land, and they were aiming for that lane.
So they sort of like cuts each other out overall?
Yeah, so whatever momentum the round had moving away from the tank had to have in the opposite direction.
Yeah, same amount of momentum, yeah.
Yeah. So therefore they could aim where they were going to land. And then when they aimed the barrel downwards, they could slow their descent slightly, because there was momentum down, so the tank would gain momentum upwards as well. Basically that was just subtracting from their momentum that they already had.
But so in real life, that can actually do that in real life?
That would work, that's physically possible, but the thing is they could only aim in the direction that the barrel would rotate in.
Yeah.
So they just happen to be very lucky to be able to aim it in that along that line. Okay, so that's my example. Collisions and explosions then. You can have two types of collision, elastic and inelastic collisions. For both of them, the total energy, that's total energy, is conserved, and also total momentum is conserved. For elastic only, kinetic energy is conserved. Okay, so distinguishing between total and kinetic there. Just if for an inelastic collision, some of the kinetic energy is converted into other forms. And an example of both types of collision, an elastic one would be gas molecules whenever they collide, and an inelastic collision would be something like a car crash. Let me elaborate on the elastic collision by giving you a little more information and a derivation for another equation you can use for that collision. The conservation, if we use the conservation of momentum for two objects, A and B, then this is your initial momentum for A, initial momentum for B, final, final. Then what I've done here is grouped the terms that apply to A. So if I subtract MA, VA, bring it over to this side, subtract B, so I get this equation. I'm calling that equation 1. So we've got UA minus VA and VB minus UB. So these are the other way around, U's and B's. Then we apply the conservation of kinetic energy because it's an elastic collision. So this is the kinetic energy initially, half times kinetic energy for the terms for A, then terms for B. Now we've got a half on both sides, so that's going to cancel out. What I do then is similar to this stage up here, is I group the A terms and I group the B terms, and then I expand out these brackets and these brackets here. So UA minus VA multiplied by UA plus VA would give me that if I multiplied it out. So I've expanded out those, and this equation we call 2. Now, from this equation, if I have MA UA minus VA divided by these terms for B, then that's equal to 1, right? So if I divide this, the right-hand side of the equation, here, that's equal to 1. Now look, these terms appear here in equation 2, okay? So I can, if I divide the right-hand side of the equation by this, then I'll just be left with VB plus UB, and I'll have 1 over this side, because I've divided these two terms are equal. And what that leaves me with is the sum of the initial and final velocity for A is equal to the sum of the initial and final velocity for B. So that equation applies to elastic collisions. If you would like to see an animation for 3 different collision and explosion types, then there's a QR code at on the last slide. You can scan that and it'll take you to YouTube animation of it. Okay, moving on. Circular motion. I'm going to start off with some dimensions for circular motion. First up, the angle moved through is the angular displacement. So there's our object there. It's moving in a circle radius r, and it moves through an arc where the angle subtended here is theta. The arc length here is equal to that angle multiplied by r. Now, that angle must be in radians for that equation. So S is equal to r theta, and 1 radian is the angle subtended at the centre of a circle by an arc of length equal to the radius. So if this were equal to r, this arc length here, then this angle here would be equal to 1 radian. So what I've said here is that if S equals r, then theta equals 1. You divide r by r, you get 1. For 1 full revolution, if that object went all the way around, then theta is equal to S divided by r, and S would be 2 pi r, that's the circumference of a circle, 2 pi r or pi d, okay? And r is equal to the radius. So therefore, theta would be equal to 2 pi r divided by r which is 2 pi. So 1 full revolution is 2 pi radians, and that's equal to 360 degrees. So if you want a conversion from radians to degrees, then 360 degrees is equal to 2 pi radians. Or pi radians is equal to 180 degrees, pi over 2 is equal to 90 degrees, and so on. Okay, moving on with circular motion. If you have constant speed in a circle, then the velocity is not constant, because the direction is always changing. So at position A, it had velocity VA, which is tangential to the circular path, and at position B, it's got velocity VB. Now, the magnitude of the velocity is the same. VA, the size of VA is equal to the size of VB, but the direction has changed, so therefore the velocity has changed. From Newton's first law, if the velocity is changing, there must be a resultant force acting on the object. And so that force we call a centripetal force, F subscript C. And that centripetal force is acting towards the centre of the circle, so that it's always, the acceleration is towards the centre of the circle. Now, it's important to remember that the centripetal force is not a type of force. So you don't have gravitational forces, normal reaction forces, centripetal forces, tension, lift, etc. You do not have that. You have these types of force that you already know: gravitational forces, normal reactions, tension, lift, and so on. And those forces can give you a resultant force that acts towards the centre of the circle, and that resultant force is the centripetal force. So this is not a different type of force in addition to all the others. Okay? Also, the centripetal force may be provided by a component of a force, such as when an aircraft is banking to turn, then its lift is perpendicular to the plane of its wings, and L sine theta would be providing the centripetal force in that case. That is if the theta is measured here, at that angle from the vertical. Right, so centripetal force is there. Some equations for circular motion. Delta V here, this was the VA that we had and the VB that we had. They've gone through an angle theta here. And delta V is the change in velocity that gets you from VA to VB. It's quite big there, but so therefore delta V is not, in this case, actually perpendicular to VA, because I've blown it up so much. But if you look at it when it's infinitesimally small, then delta V would be perpendicular to VA. Okay? Now delta V is directed towards the centre of the circle if it acts from the midpoint of VA and VB. Centripetal acceleration is equal to delta V over delta T, because acceleration is the change in velocity over the change in time. And A, from there you can get A is V squared over R. If you have a constant mass, then centripetal force is mass times acceleration, so force is equal to mv squared over r. Okay. That comes from Newton's second law if you have constant mass. Frequency, the number of oscillations completed per unit time is equal to 1 divided by time period, time taken to complete one full revolution. And the average speed is V is 2 pi r over t, which is also equal to 2 pi r f from that equation there. So those are some of your equations that you'll need to know, be able to apply in circular motion. Okay, when an object completes a loop, the loop. Now, when I say the centripetal force changes, what I mean there is that the forces that are providing the centripetal force change as it goes around the loop. So it's not always the same force in this case. And so the normal reaction of this object on the track is always going to be acting towards the centre of the circle, but the weight acts vertically downwards. So the weight is not always going to be acting towards the centre of the circle, and that's why the centripetal force will change. So let's look at it as it moves around the loop. Position 1, at the bottom, the weight is acting away from the centre of the circle. But the normal reaction is still acting towards the centre. So the centripetal force is N minus the weight. The normal reaction minus the weight. Position 2, the weight is tangential to the circle. So it's neither adding nor subtracting from the centripetal force. So here it's equal to the normal reaction. Up the top, the weight is towards the centre now, so it's adding on to the centripetal force, so you've got N plus W. And then position 4, the weight is tangential again, so similar to 2, you just have N providing the centripetal force. Okay? And if you consider friction, friction is always tangential to the circle, so that shouldn't add to your centripetal force or take away from it. This, at position 3, when it's right at the top, the instant it's at the top, the minimum centripetal force would be provided when N is equal to 0. So if N equals 0, then it's just the weight providing the centripetal force. Right. If you have, so from there you can get a condition by which you can just complete a loop, i.e. don't fall off the top there. And so the condition is that the centripetal force at the top is just equal to mg. And from there, if that's providing the centripetal force, then it's equal to the F from F equals mv squared over r. And those m's will cancel out, so v squared is equal to gr. And so that v there is the minimum speed required at the top for you to complete one loop. Alright? That's your minimum speed. V squared equals g over r. Got a question?
Yeah, so you know when it said N equals 0, does that mean that it wouldn't be touching the actual track itself? Because if you see contact, it has to have the actual force, doesn't it?
Would it be in contact? I think it could be in contact, but there's no. If it's moving tangential at that point, then there would be. If it's moving perfectly tangentially, then there would be.
It's a little rub. It's not really touch. It's a little rub.
Yeah. Well, I mean, rubbing is not quite the right word anyway. Because
Yeah.
you're talking at the atomic level.
Okay.
It's providing
Okay.
normal
Question. Why do we feel weightlessness at the top?
That was, yes.
Because you're being accelerated at g at that point. If n is 0, then you're not feeling any other force apart from your weight. So it's like you're just dropping. In fact, you just drop for a moment in that case before the velocity pushes you back into the track. So you begin to drop, but because you have that velocity, that brings you back to the track.
So could you define weightlessness, please?
Can I define it?
Yeah, because in the previous mock, if we did before, it came up and I didn't know what to say.
So if you're, I guess the way to do that would be when your acceleration is equal to g. When your acceleration is equal to g.
Okay.
Okay, so a is equal to 9.8.
Okay.
If you accelerate that.
When
So
not-
your resultant force is equal to the weight, your weight.
Okay, when you're...
Okay, that's what's happening during the loop. Now we're going to use that condition to find out what's the minimum height on this track that we could roll our object from for it to complete one loop. I think I've actually got my velocity pointing in the wrong direction, but just ignore that. Okay?
Which direction should it be?
The other one.
The other way, because it's going to go up here and down there. But you get the point. Right. So the condition to complete just one loop is that v squared equals gr, and the energy that the object has here is purely gravitational potential. It's not moving, so there's no kinetic. And then it's equal to mgh, h being the height here that it's being dropped from. Energy at position 3, when it's at the top of the loop, is equal to the potential that it has, because it's above our reference point here, plus the kinetic energy that it needs in order to complete that loop. Now, the loop has a radius r, so therefore the height of the object at position 3 is 2r. So therefore the kinetic energy half mv squared, and the potential is mg times 2r. If we follow on from that, the energy at position 3 is half mgr. Now what I've done there is substitute rv squared. V squared is equal to gr, so I've substituted that in there, okay? And then just brought the 2 in front. So we've actually got 2 mgr. That's the energy if we multiply everything out. 2.5 mgr. So that's the energy at position 3. From the conservation of energy, E1 equals E3. So mgh equals 2.5 mgr. The mg's will cancel out, so we get h is 2.5 r. So you have to, this height has to be 2.5 times the radius in order to complete one loop.
Is that for all scenarios, just for this example?
All scenarios of what?
For example, if you're making a roller coaster and do the loop, has your height got to be 2.5?
Yeah, that's the minimum, and this is assuming no energy losses. In a real loop-the-loop, you go to Alton Towers or whatever, you're going to have friction, so you're going to have to account for that as well. You could do experiments to work out roughly how much friction there'll be, and then add in a safety margin as well. Okay? Gravitational fields then. We illustrate gravitational fields with field lines, and field lines always leave surfaces perpendicular to the surface. So this is a radial field here. We've got a circular object, or spherical object, and the field lines are leaving that surface perpendicular to the surface. And you can see therefore that as you move away from the object, the field lines are further apart, therefore the gravitational force that you experience further away is smaller, or the gravitational field strength is smaller as you move away from it. So that's a radial field. That applies to point masses, and we also use that for larger objects like planets and so on. Uniform fields are the other type of field you can have, and the Earth's gravitational field approximates to a uniform field as long as you're close to the surface. So let's go close to the surface of the Earth. And when you're close to the surface of the Earth, the gravitational field strength is 9.8 newtons per kilogram. Strictly speaking, it's not uniform, it is slightly radial, but approximates to uniform. Okay, orbits. Now what I've done here is, you can consider Newton's work on gravity and so on first, but chronologically Kepler came first, right? He was a German astronomer, and he did a lot of work with Tycho Brahe, and he discovered 3 laws of planetary motion. Firstly, planetary orbits are elliptical, but they are very nearly circular, with the Sun at one focus. Planets move in such a way that an imaginary line that joins the planet and the Sun sweeps out equal areas in equal time. And the third law, which you need to know, those 2 you don't need to know, the squares of the orbital periods of the planets about the Sun are directly proportional to the cubes of their mean distances from it. So, i.e., t squared is proportional to r cubed. Okay. Kepler could not go beyond that third law, right? So let's now move forward in time to Newton's work on gravity. Newton lived in England 1642 to 1727. Right, first thing, what do we mean by gravitational field strength? You need to get this right. This is the definition for gravitational field strength. The force exerted per unit mass placed at that point. So G equals F divided by M. Don't use it from G based on the law of gravitation. Newton's law of gravitation is that. I'm not going to read it all out, you can read it in your own time. And if you express it mathematically, F is minus G M1 M2 over R squared. Now G is the universal gravitational constant, 6.67 times 10 to the minus 11. That is in the formula book. And R is the distance between the centres of the masses, M1 and M2. So from there, because G is equal to F divided by M, and F is equal to this expression here, then G being F over M is equal to G M over R squared divided by M. That's where that equation comes from. This is not the definition, that's the definition of gravitational field strength. But this follows on from those two. Okay? So again, you can see G weakens as you move away, and it weakens according to an inverse square law. Right? Oh, and I should say as well that it was Henry Cavendish that came up with the best value for G, the first best value for G, the universal gravitational constant. He wasn't actually setting out to calculate G, he was setting out to calculate the density of the Earth, but he, as part of that, worked out the best value for G. The experiment was popularly known as weighing the Earth, if you want to research that. Okay, so onto planetary orbits then, and here we start to see some links with or how Newton built on and confirmed Kepler's work. Centripetal force for a planetary orbit is provided by a gravitational force, and that's what Newton appreciated. And from the gravitational force equation that Newton derived, if Fg is providing the centripetal force, then Gm over r squared is equal to mv squared over r. So v squared is because the m's cancel out here, okay, and one of the r's cancels out here, then v squared is equal to minus gm over r. And we know the average speed is 2 pi r over t. So if we square both sides of the equation, v squared is equal to 4 pi squared r squared over t squared. We can then substitute that in for v squared over here. So we have this, and t squared is equal to 4 pi squared over gm times r cubed. And because all of the terms in the brackets are constants, 4 pi squared is obviously constant, this is the universal gravitational constant, this is the mass of the Earth, then t squared is proportional to r cubed, which is what we saw from Kepler's third law. Yeah.
Is it the time period for one oscillation or one orbit?
Time period for one orbit. Yeah.
Okay.
Okay? So that's how Newton confirmed Kepler's third law. I'm going to give you some calculations based on an example orbit, and I'm going to use the International Space Station for that. That's a picture of the International Space Station taken by the crew of Space Shuttle Atlantis, as they, I think it was as they were departing from the ISS. So, the International Space Station has a mass of 450,000 kilograms, and it orbits at a height of 423 kilometers above mean sea level. what we want to do is firstly calculate the gravitational field strength at that height, calculate the speed at which it needs to orbit Earth at that height, and then calculate its orbital time period. I have actually got some interesting questions on this based on the film Gravity. If you check out my Twitter feed, you see. It was quite a long time ago I posted that. Okay, first thing is, in our equations that involve R, we're not going to use 423 kilometres, because that is 423 kilometres above mean sea level. So the R needs to go to the centre of the orbit, which is the centre of the Earth. So we need to add on the radius of the Earth. So R then is 423 times 10 to the 3, because it's kilometres, not metres, plus 6.4 times 10 to the 6. So that's our R value. First calculation, G is GM over R squared. Plug your values in. Always show your substitutions when you're writing down your equation, working out. So show how you've substituted the values in. Sometimes that's important for getting marks correct. And what we find out is that G is equal to 8.60 newtons per kilogram. Okay? That's a sensible value. It's a sensible value for that height. So that's the gravitational field strength at that height. Now we want to calculate the speed at which it needs to orbit the Earth. So how would we do that? Well, the centripetal force is provided by the gravitational force. Now you could use Fg equals gmm over r squared. However, we already know what the gravitational field strength is from here, so we can just do gravitational field strength times the mass. That's from the definition of gravitational field strength. So, the centripetal force is equal to the gravitational force, and you'll see that the m's cancel out here, so v squared is equal to gr. You've seen that before. That's equation for v squared. Put the values in here, and we calculate 5.87 times 10 to the 8. That's incredibly fast, right? Faster than the speed of light. So that is not the velocity, right? You have to remember to square root it. Very common to forget that last step. Now I've stated that in kilometres per second. So 7.66 kilometres per second. And when I was collecting the data for the International Space Station, I just checked that I calculated the value that was sensible and it is. Okay, so 7.6 kilometres or 7.7 kilometres per second. And then we want to find out the orbital time period. And we just need to use the average speed equation here. We know what V is. We know what R is. So we just rearrange that for T. T is 2 pi R over V. Put your values in again. You could state 5,594 seconds, but much more sensible to state it in minutes in this case. So 93 minutes. Yeah.
So it takes less than a day to orbit the Earth?
Yeah. Takes less than a day.
Are you serious?
Yeah, I'm serious. Takes an hour and a half. That's an hour and a
That's
half.
what I was thinking, like.
Yeah. It's moving fast.
Oh.
It's not very, very high.
Okay.
Yeah.
Are there people inside it?
There's people inside it, yeah. That's right. We're moving very fast right now.
Oh yeah. We don't feel it.
Yeah, just don't feel it because the relative motion between us and the surface of the Earth
Yeah.
is 0, usually. And relative velocity between the astronauts and the ISS is 0, so it's fine.
Okay.
Okay, yeah, it does only take an hour and a half. There was a video made a year or two ago in recognising, okay, can't remember his name now, first cosmonaut into space, who was a Russian cosmonaut, and his name evades me now, Yuri Gagarin, I think it is, that's right. And the International Space Station filmed looking down onto the surface of the Earth to, did you see that, yeah? So it's what he would have seen, or similar to what he would have seen anyway. Yes?
You know the Earth, yeah, it spins one direction, yeah?
Yeah.
Well, what happens if you walk the other way, you don't feel anything?
Yeah, but the relative velocity between you and the surface of the Earth is 0, so your momentum is in the same direction as the Earth, so you just walking in the other direction.
So is that why when we jump, the Earth doesn't move? Because we move
Yeah.
with it because we've got the same
When you
velocity.
jump, or whilst you're standing, before you jump, you have the same velocity as the surface of the Earth. So when you jump up, you will actually be doing a little bit something similar to projectile motion. But because the surface of the Earth is moving with you, you don't recognise that.
But saying that, sir, you know when you in a car and you've got okay, sir.
Okay, geostationary satellites. These are satellites that stay above the same point on the surface of the Earth. Okay, so they're always above the same point. In order to do that, it must move at the same rate as the Earth rotates, which is 24 hours. Okay, T must be 24 hours. And that is only possible if you are above the equator, travelling west to east. So the Earth's surface is rotating towards the east, which is why the sun appears to rise from the east. It's moving towards the east, so you've got to be going in that side direction. Only points on the Earth's surface at the equator move in a circle with the centre of the Earth at the centre of that circle. And that's why you've got to do it above the equator. The poles, for example, they don't move in a circle, so you can't move in a circle matching that. And geostationary satellites are useful for things, for example, in communications, so that you don't have to track, or the satellite dish doesn't have to track the position of the satellite through the sky. Okay, so it can just continue pointing in one direction, so you don't have to worry about thinking where the satellite's going to be and then having the machinery to move the satellite. You just keep it pointing in the same direction. The satellite's always going to be there. And if you would like to see the video animation for collisions and explosions, that's the QR code that will take you there. And that is all for today.
So I can stand on your iPad.
Sorry?
Stand on your iPad.
I could, yeah.
And then,
Yeah.
oh.